Välkommen till Kungliga Vetenskapsakademin och den här presskonferensen då vi ska presentera årets Nobelpris i kemi. Welcome to the Royal Swedish Academy of Sciences and this press conference where we will present this year's Nobel Prize in Chemistry. We will keep to our tradition and start the presentation in Swedish and then continue in English. And you are of course welcome to ask questions later on in either language. Jag heter Hans Ellegren och är ständig sekreterare här på Kungliga Vetenskapsakademin. På min ena sida sitter professor Heiner Linke, ordförande i Nobelkommittén för kemi. Och på andra sidan professor Olof Ramström, ledamot av Nobelkommittén för kemi och sakkunnig inom ämnet. My name is Hans Ellegren. I'm Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Heiner Linke, Chair of the Nobel Committee for Chemistry. And to my left, Professor Olof Ramström, member of the Nobel Committee for Chemistry and one of the experts in this field. Årets pris handlar om att skapa nya rum för kemin. This year's prize is about creating new rooms for chemistry. Kungliga Vetenskapsakademin har idag beslutat att utdela 2025 års Nobelpris i kemi till Susumu Kitagawa, Kyoto University, Japan, Richard Robson, University of Melbourne, Australien, och Omar Yagi, University of California, Berkeley, USA, för utveckling av metallorganiska ramverk. The Royal Swedish Academy of Sciences has today decided to award the 2025 Nobel Prize in Chemistry to Susumu Kitagawa, Kyoto University, Japan, Richard Robson, University of Melbourne, Australia, and Omar Yagi, University of California, Berkeley, USA, for the development of metal organic frameworks. Professor Heiner Linke will now give us a short summary in English. Please.
Yeah, ladies and gentlemen, we have a great prize for you today. Imagine that the tools of chemistry could be used to create entirely new materials with unheard of properties. For example, imagine we could make solid materials full of tiny spaces in which gas molecules can feel at home and with chemical properties that can be adjusted to the specific needs and wishes of different molecules. One could then imagine to create materials that can separate carbon dioxide from air or from industry exhaust pipes, or that could be used to separate toxic molecules from wastewater. One could imagine making materials that can harvest water molecules from dry air and make potable water in a desert, or materials that have catalytic properties on their inside so that toxic gases could be absorbed and then transformed into unharmful substances. This year's laureates have achieved just that. They have found ways to create materials, entirely novel materials, with large cavities on their inside, which can be seen almost like rooms in a hotel, so that guest molecules can enter and also exit again from the same material. A small amount of such material can be almost like Hermione's handbag in Harry Potter. It can store huge amounts of gas in a tiny volume. This type of materials, called metal organic frameworks, can be created with almost unlimited variations, creating unending possibilities for the greatest benefit to humankind. Thank you.
Thank you, Heiner. Professor Olof Ramström will now give us a more in-depth presentation of this year's Chemistry Prize. Please.
My privilege. So, well, this year's award is a story full of holes, but with enormous capacity to absorb all your attention and other things. So this year's award is about frameworks, as we heard. And here you can see a typical construction framework. It happens to be made from wood, where the wooden boards or planks are joined together, assembled, probably using metal nails or screws. And of course, this makes up the skeleton of this construction or this future house, but you can actually see hinted here the many rooms inside this framework. So imagine now how we would be able to make such a framework at the molecular scale. And instead of using metal nails or wooden boards, we would use ionic or atomic molecular nodes and linkers and let them assemble themselves in such a framework. And this is exactly what our laureates have been working with. They have adopted a type of chemistry where you use metal ions or metal clusters as nodes and link them together with organic compounds. Organic compounds are such that are made from containing carbon-based molecules. So we have the metal ions as nodes, and then we have the organic molecules as linkers. And once you have identified those and mixing them together, they will then find themselves and arrange themselves in a type of self-assembly process into an ordered framework, a metal-organic framework, as you can see here. Now, this may look quite straightforward when you see it like this. However, to build such ordered structures was a very, very difficult challenge for many, many years. And although we actually knew about structures that look like this, how to actually predictably being able to make them was very elusive. But let's go back to the late 1980s. At that time, Richard Robson, he reasoned that it would indeed be possible to build such frameworks predictably by taking metal ions and molecular organic linkers. He was inspired by the structure of diamonds, as you can see here. And if you know, diamonds are based on carbon atoms, and each carbon atom in diamonds are surrounded by 4 other carbon atoms in a pyramidal or tetrahedral orientation or shape. And as you can see here in red. So Richard Robson reasoned that if you take a metal ion, in this case copper 1, as you can see here in purple, acting as nodes, and mix that together with an organic molecule, which is also pyramidal shape or tetrahedral shape. You can see it here in yellowish white. And in this case, each arm of this molecule, this organic molecule, has a so-called nitrile group. And the copper ion and the nitrile groups, they can find each other and form bonds. And that will, in principle, lead to a structure that would be similar to the structure of diamonds. Well, contrary to the general expectation at that time, in the late 80s, this actually worked really, really well. And Richard Robson obtained such an ordered framework structure, as you can see here. Now, in contrast to diamond, to the structure of diamonds, where the carbon atoms are very, very tightly packed, this framework, however, contained cavities or holes. As you can see, relatively large cavities or holes. And when you make this material, these cavities will be filled by, we call them inclusions, compounds, in this case solvent molecules, and also negatively charged ions, what we called counter ions. Once having showed this work, this demonstrated that this is indeed possible, Richard Robson also reasoned, he came up with several principles and discussed different features of such material. He, for example, discussed how to modulate such materials to make them more strong, how to keep together more strongly, to make the cavities smaller or bigger. He also predicted some applications of such materials, such porous materials. He also was able to show one such application. He was actually able to replace those negatively charged ions I mentioned with other ions in a common process in chemistry called ion exchange. And he could do this without the material collapsing in the process. Now, this is all about porous materials. And one of the absolute most important applications of porous material is gas adsorption. And so we're jumping ahead a few years. And Susumu Kitagawa, he managed to demonstrate that gas adsorption is indeed possible in these materials. So he designed and produced a relatively complex framework, as you can see on this picture. And this framework, too, contained cavities or channels. You can see them here in yellow. That when you make this, network framework, they were actually filled with water. However, this time, this framework was stable enough, so when you remove the water from the cavities, from the channels, the material was still intact. It did not disrupt in the drying process. So now you had a material that was empty, and that could be used to adsorb, to take up gas molecules in a gas adsorption process. And Susumu Kitagawa could show this for several gas molecules, such as methane, oxygen, and nitrogen. He could show that the gases could be taken up, adsorbed by the material, and could also be released from the material, desorbed from the material reversibly. So by now, if you look at this structure, we now had frameworks. The development had come so far, so we now had frameworks that were stable enough to endure to emptying the pores, to emptying the channels and cavities. However, because of the principle of making these structures using metal ions, clusters, and organic linkers, Susumu Kitagawa reasoned that there is another feature with these materials. He then predicted that not only can you make such stable materials that can take up gases, you can also have this material changing shape upon changing the conditions. And you can see that. So in that case, you will get this kind of shape-shifting, flexible metal-organic frameworks. And you can see an example here where you have one shape where you have gases inside the cavities of the material, and then when you remove the gases, you have a different shape of the material. Now, at around the same time, a very important breakthrough was made by Omar Yagi. So Omar Yagi had been working for several years to try to make highly stable metal-organic frameworks. He was looking for methods to make them more stable. And he reasoned that if you use one of those metal clusters, as you can see here on the left-hand side, this is a metal ion cluster based on zinc ions and oxygen atoms. And if you take that cluster and you mix that with organic linkers that contain carboxylate groups, then you would get a very stable construction. And he could show that in this structure, this metal-organic framework, which was denoted MOF5. And as you can see, this framework is a cubic framework. You have lots of cubes stacked upon one another. And you can also see that this is a very porous framework, and you can see the cavities or the inside the framework symbolized by these yellow spheres. Now, this is an astonishing framework because it was highly stable. It was stable all the way up to 300 degrees Celsius, heating up to 300 degrees Celsius. But even more remarkable with this material was that it contains an enormous surface area. So just a few grams of these porous materials, roughly the same amount as a small sugar cube, a couple of grams, contained as much surface area as a large football pitch. That is several thousands of square meters, right? So in a sense, that's exactly what Heiner mentioned before. This is a little bit like Hermione's handbag, small on the outside, but very, very large on the inside. And what this also showed is that this material are very, very suitable to absorb large amounts of gases and other molecules. And this became an eye-opener for the entire field. So not only did people coming in the field from outside of the field, but also industry became very, very interested in these materials. A few years later, Omar Yaghi made a conceptual contribution, important conceptual contribution. So because metal-organic frameworks are based on organic linkers, organic compounds, and organic compounds can be varied almost infinitely. That means that you can change the metal-organic frameworks just by changing the linker, the organic linker. And you can do this without changing the basic structure of the metal-organic framework. And you can see an example over here. You can see that the cavity volume has increased by just changing the length of the organic linker. And you can do that without changing the general structure, in this case the cubic structure, of the metal-organic frameworks. So by doing this, you can build large families of MOFs with the same structure, with different properties. You can also think of actually modifying the linkers, so you can add, for example, catalytic groups, or you can, in that way, change the properties of the materials that way. So after following these fundamental great breakthroughs from our 3 laureates, this field evolved very, very rapidly, and many, many structures were developed over the years to come. Many thousands of structures have now been developed and applied. I will just show you a few examples. As you can see here, so for example, now we have MOF structures, metal-organic frameworks, that can capture water from air, as Heiner also mentioned. For example, dry air in deserts, and those can then be used to produce drinking water. We have metal-organic frameworks that are good at capturing carbon dioxide from, for example, industry effluents. We have metal-organic frameworks that can store large amount of hydrogen gas, and frameworks that can be used to recover precious rare earth metals from waste. We also have frameworks that can remove and break down oil contamination. And we have frameworks that can extract forever chemicals, such as PFAS, from water. These are just a few examples, and the list goes on and on and on and on. But overall, through these fundamental breakthroughs from our 3 laureates, this has led, and also their continuing efforts in this field after the breakthroughs, this has led to a very, very rich and active area where we see new metal-organic frameworks developed almost every day. Right? And many of these frameworks have also been applied, as you saw here. And it's very, very clear that we will expect many more frameworks to be developed and many more applications in the future for the benefit of humankind. So, thank you.
Thank you, Olof. Let's see now. Do we have Professor Kitagawa on the phone?
Yes.
Good evening, Professor Kitagawa. Again, our warmest congratulations to the Nobel Prize in Chemistry.
Good evening. Thank you very much. I'm deeply honored and delighted that my long-standing research has been recognized. Thank you very much.
I know that you are very busy tonight, but do you have a few minutes to take some questions from the press here, the media? We have this press conference right now where we have both national and international press. So can you take some?
Okay. Yes.
SVT, Swedish Television.
Good morning, Professor Kitagawa.
Okay.
My name is
Good morning.
My name is Susan Ritson, and I work for Sveriges Television, Swedish Public Service Television. I want to congratulate you on your achievements.
Thank you very much.
I was wondering, science aside, what were your thoughts when you received the news just a short while ago?
Yeah, this is the just I heard this introduction of our works, and this is very new materials, so it's a long time to realize in our society that this is real, the porous materials. That is very big effort to do it. But meantime, I really enjoy the chemistry of these materials. So this is my feeling, and so once again, I'm deeply honored and delighted, and my long-standing research has been recognized. And I think the Omar Yagi also think about this.
I know Professor Olof Ramström mentioned that your discoveries gives us hope. Do you agree? And what are your hopes for the future with the MOFs?
Yes, I'm very much interested in transform this material to the society, of course, but this material is also a kind of surprising properties. So this is my fun to discover new properties depending on the softness and also the several and the new characters of and the properties of these framework materials.
Okay, next question.
Omedetou gozaimasu. Omedetou gozaimasu.
Arigatou gozaimasu.
I'm Anneli Megner-Arn, TV4. I'm wondering, would this technique make it cost efficient to suck out carbon dioxide from the air to help fight climate change?
Yes. Yeah. So the properties of these materials is the sort of the well-defined porous structure. So that means the surface of the pore can strong interaction with the CO2, but this interaction is in a scientific word that is the physisorption. So the interaction energy is not so strong. So that means easy to capturing these materials, but easy to release this material. So energetics is quite the important for this technology. So this material can realize it. I think it.
Okay. Hello, Mr. Kitagawa.
Yes.
It's known that MOFs shows great potential in gas storage and catalysis, but mass production remains costly. What technological breakthroughs in the next 5 years could truly advance their commercialization?
Yeah, we are thinking about with my startups. And in the world, for instance, in the energy materials and the methane, in that case, for instance, well-developed countries, still difficult to have pipelines all over the country. So this means we need to still have the cylinder or something for the store this methane materials, but it's very heavy because the high pressure cylinder we use. This is 100 years tradition. So by using these materials, we can make this cylinder is lighter and lighter and easy to deliver to any places. So this is a reality in the next 5 years, I think.
We have a Polish TV here.
Hi.
Hello, Professor. This is Bogumir Radzieski from the Polish television. Congratulations. I wanted to ask you, because what's so amazing about the metal organic frameworks is the wide variety of applications they have already found. I'm wondering, in what field do you find most important or possibly most promising for the future in terms of practical applications of MOFs?
Yeah, my dream also, this is not realized. My dream is to just handle the air, because air contains CO2, oxygen, and the carbon elements, oxygen elements, nitrogen elements. That means, for instance, if you think about your body, proteins contain carbon, nitrogen, oxygen. And also fuel contains carbon, hydrogen, and something. So air contains most of the elements for our important materials. So my dream is to capture air and separate air to, for instance, in the CO2 or oxygen or water or something, and convert this to the useful materials using the renewable energy. Okay, so even if we obtain the fuel from the air, so fuel is combusted into the air, but we can still the reuse of this air. So that cycle is quite important for our society and also our planet. So this is my dream, and also we have to realize it using this kind of porous materials. This is my answer.
We have a question here, please.
Hi, Professor Kitagawa. This is Yue from Chinese media, The Intellectual. My question is, how persistent is materials created using this framework? Will it dissolve soon, or could it last for centuries? And what is the environmental implication of that? Thank you.
Yeah, and first of all, I have to say I'm very enjoying, even I have a very difficult situation. So creating new materials is very important.
We might have lost him there. See if we can make a new try. We give it a few more seconds a chance here.
Hello?
Hello, yeah. Now you're back here. Maybe we should take a new question. That's probably easiest. Over there.
Okay, so...
Hello. Do you hear me?
How long I have to stay here? How long? Because I have to go out for the meeting.
Okay.
So
I have
how
one
long?
last question.
5 minutes? Okay, sure.
Okay, I'm from the Swedish media magazine called Forskningen Framsteg. I would just like to know, what was your, did you anywhere during all these years of research hesitate or doubt that you would manage to create these frameworks? And what was the biggest challenge, the threshold that you had to manage? Can you say something about that?
Yeah, so the advent of this material, we have already current material. We have activated carbons, zeolites, and so on and so forth. So we have to show this material is quite stable, even without gas molecules. So this is a very tough time. So but I was so optimistic because the create of new material is very, very much fun. It's very challenging. So anytime I told to the students in the challenge is very important in the chemistry and science. So that's a point in I recall I look back this time.
Okay, we take one final question there, please.
Oh, final, okay.
My name is Riko Takahashi and Kyoto News Japan. I say even in Japanese, おめでとうございます. And then if you said you are short of time, so I just do simple questions. Where were you when you got, I have two questions. Where were you when you got a phone call from the Nobel Committee? And
first answer.
And,
very surprising.
I continue.
Very surprising.
Oh,
very surprising and
now?
also very pleased. Yeah, very happy. Because this is a long-standing chemistry. So this is recognized. This is my I'm pleased to know that. And maybe we can share the feeling with the Omar and Richard.
Okay, Professor Kitagawa, I think that's the final question. Thank you for your important answers here, and we look forward to see you here in Stockholm in December.
Yes, I will. Thank you very much. Thank you.
Thank you. I can inform you that we were able today to reach all 3 laureates, so they have been informed. Now there is time to ask any further question that might be to the prize committee about their work or something else that is related to the Nobel Prize in Chemistry. Are there any further questions?
Could you tell us how Mr. Robson and Mr. Omariyagi reacted when you announced them the prize?
They were rather glad. They were surprised, of course, as all laureates are, essentially all. But of course, this is a very staggering moment for someone to get a call like this, and they were really happy.
Thank you. My name is Lisa Melton from Nature Biotechnology. Is there any indication that beyond industrial uses they may be considered for biology, for medicine, medical devices, and so on?
Olof?
Yes, that's a very good question. And there have been a lot of work going on in this field to look for the biocompatibility of such materials and also finding applications for such materials in biology. So, for example, there have been many efforts trying to use these materials for example, drug delivery applications. And also you can use these materials for imaging and for diagnosis. There have been many attempts to do that. And I would say that, of course, we are not really there yet to have final products for this, but there is a lot of research going on in that field, yes.
I think that might be it. Thank you for your interest coming here. We hope to see you back here at the Academy on Monday when we will present this year's prize, Sveriges Riksbanks Prize in Economic Sciences in the memory of Alfred Nobel. Thank you.